Instantaneous rate of change. Let's start off by revisiting our example that contains the possible graph of traveling 100 miles within 2 hours. How can we obtain a more accurate approximation of the rate of change? First, we have to determine at what time of travel we are looking to approximate. Suppose we were looking for the best approximation for the rate of change at 15 minutes. What should be the values of time 1 and distance 1, as well as time 2 and distance 2, which would give us the best approximation? We could start by putting time 1 and distance 1 at the 15-minute mark, and then we could put time 2 up here at 1 hour and record that distance. Or would these points give us a better approximation, still time 1 being at 15 minutes, but then maybe time 2 is between a half hour and an hour, closer to the hour, so probably at about 50 minutes or so? How about these points, still at 15 minutes, but then more closer to 40 minutes as time 2? Here's another graph that has time 2 even closer to time 1. How close should our points be for the best approximation? The closer time 1 distance 1 and time 2 distance 2 get to one another, the better the approximation is. With this in mind, mathematicians were able to solve the tangent line problem. If delta x, or the difference between x values or t values in this example, could be as close to 0 as possible, it wouldn't just give us an approximation, but an instantaneous rate of change, which is representing the slope of a tangent line at any x or t value. Let's revisit our difference quotient. The slope of a secant line is equal to f of x plus delta x minus f of x, all divided by delta x. If we let delta x be replaced with h to represent the horizontal change between the x values, the slope of our secant line becomes f of x plus h minus f of x, all divided by h. Now rewrite the difference quotient to represent the slope of a tangent line instead of a secant line. What would h need to approach, and how could we do that? The value of h would need to be 0, but that doesn't work in our formula. We would get division by 0. And this is where limits come in handy. As h approaches 0, we can find the instantaneous rate of change, or the slope of that tangent line. So to find the slope of that tangent line, we are going to take the limit of f of x plus h minus f of x, all divided by h, as h approaches 0. If the limit above exists for the function f, then the line passing through x comma f of x with the slope of m tangent, or slope of the tangent line, it is the tangent line to the graph of f at the point x comma f of x. Let's try an example where we're finding the slope at a point. Find the slope of the graph of f of x equals 2x minus 1 when x is 2. Let's start by setting up the difference quotient, where we have f of x plus h minus f of x all over h. And then from there, we are going to substitute 2 in for x, so we have 2 plus h minus f of 2 all divided by h. And in order to find the slope of the graph, we are going to be finding the limit of this as h approaches 0. The next step is to substitute our 2 plus h and our 2 into the actual function where the x occurs. So we have 2 times 2 plus h minus 3, and then we're going to subtract 2 times 2 minus 3. And then again, we're all going to divide it by h, and we're finding the limit of this as h approaches 0. By simplifying through the use of the distributive property and evaluating expressions, we would get 4 plus 2h minus 3 minus, well, 4 minus 3 is 1, all divided by h. And again, we're taking the limit of this, or finding the limit of it, as h approaches 0. The next step is to finish simplifying. We can see that 4 minus 4 is 0, so they cancel out. So we're finding the limit of 2h divided by h as h approaches 0. Well, the h's also divide to be 1. So we can rewrite it as the limit of 2 as h approaches 0, which is equal to 2. So we were able to find that limit. Let's try another example. This time we're going to find the slope of the tangent line to the graph of f of x is equal to x squared plus 2 at the point 0, 2. We're going to start by writing out the difference quotient, which is f of x plus h minus f of x all divided by h, and we're going to take the limit of this as h approaches 0. And then we can substitute 0, which is our x coordinate, in for x. So we have the limit of f of 0 minus h minus f of 0 all divided by h as h approaches 0. Next, substitute the function into the difference quotient with the x value of 0. So we have f of, instead of x here, it'll be 0 plus h squared plus 2, and then minus 0 squared plus 2, all divided by h, and we're taking the limit of this as h approaches 0. The next step is to simplify what's in the brackets and parentheses. So 0 plus h squared is just h squared. We still have the plus 2, and then we have 0 squared, which is 0, plus 2, which is 2. And we're subtracting this value of 2 here. And we're taking the limit of h squared plus 2 minus 2 divided by h as h approaches 0. Well, we know that positive 2 minus 2 is equal to 0. So we now have the limit of h squared divided by h as h approaches 0. And then we can divide h squared by h, so it's just h. So the limit of h as h approaches 0. Now we can use direct substitution to get the limit value of 0. So therefore the slope of the tangent line to the graph f of x equals x squared plus 2 at the point 0, 2, the slope of that tangent line is equal to 0.